Hello, everyone, and thank you for joining our third Amazon DocumentDB Focus Day of 2023 to discuss data modeling methodology for Amazon DocumentDB with Mongo compatibility. My name is Jason Plank, and I'm a go-to-market specialist on the DocumentDB service team. I've been in the industry for about 20 years and have held various roles such as product manager, management leader, development leader, and obviously my role at AWS as a GTM specialist. And I've been on the DocumentDB team for about a year and a half. I'm also going to pass the microphone to Mihai, who will lead much of today's discussion so that Mihai can introduce themselves as well. Mihai?
Thank you, Jason. Hi, everyone. My name is Mihai Aldoiu, and I'm a specialist solutions architect for Amazon DocumentDB at Amazon Web Services. I've been a solutions architect for almost 2 years now, and I've been helping our customers deploying their workloads using Amazon DocumentDB in an optimal fashion.
The agenda for this talk includes a brief introduction into why document databases are a good choice, introduce the NoSQL data modeling concepts, and of course, we'll go over the methodology and the steps to take in order to design the optimum schema for each use case. Our first topic will go into why document databases and just a little bit about Amazon DocumentDB. AWS has a broad offering of cloud services across databases and analytics, and the service you use will typically depend on the use case. We refer to this as purpose-built, meaning the service you use will correspond to your specific use case. Broadly speaking, as you look across our portfolio, we offer relational databases, and those services are for customers that want to move away from self-managing Oracle, SQL Server, MySQL, Postgres, and MariaDB databases. For this, AWS offers Amazon RDS and Amazon Aurora. For customers wanting to move away from self-managing non-relational document and key value stores such as MongoDB, Redis, and Memcache, AWS offers DynamoDB, DocumentDB, and Elasticache. And in addition, in the NoSQL family, we offer Amazon Neptune, which is a graph database, and that allows you to store data as relationships, enabling you to build queries that efficiently navigate highly connected data sets. For wide column databases, we offer Amazon key spaces. In this service, you can store a large number of arbitrary columns in each row. When it comes to document databases aggregate and are optimized to store data into hierarchical structure represented in JSON format. For this talk today, we will focus on document database modeling, as these are probably the closest to an all-purpose NoSQL database and closest to a relational database. We often talk with customers and they ask us why document databases. So that we thought that this would be a good opportunity to talk a little bit about why. One of the first reasons is that data is stored in a JSON data format. So as we're storing data in that format, it's easily structured. It maps naturally to how we think about modeling data in our applications. We typically don't model data in a tabular format in our heads. We're thinking about groups of things instead. The next area is around flexible schema and indexes. So dynamic schemas can change depending on our data needs and access patterns. There's no need to design complicated or rigid schemas. Indexes can be created and dropped in on demand, and that could be to meet changing application requirements or query patterns. These can also be declared on any field within your documents, including fields nested within arrays. Another big reason for document databases is ad hoc query capabilities. In document databases, you're able to retrieve specific fields and values, and even regular expression queries. DocumentDB, as an example, uses a JSON kind of query language, so it's really easy to learn. The next part that we'll talk about on the slide is really revolves around use cases. Amazon DocumentDB use cases are wide and many, given that document databases offer both flexible schemas and extensive query capabilities. The document model works well with use cases that require complex documents that are dynamic and may require ad hoc querying, indexing, and aggregations. Some common use cases include content management. Uh, much of the content that we read today, from news articles to blogs to recipes to patient records, all of that data lends itself really well to a document model since it's dynamic and changing. Another example of use case are mobile use cases. It's very easy to store the data you're collecting going back and forth between devices, because lots of times in the mobile world, this is JSON data that we're talking about. So naturally, a JSON data store makes a lot of sense. The next use case that we commonly hear about are catalogs. This is all about being able to record the output of machine learning experiments, inventory descriptions, pharmaceutical trials. We see a broad set of customers that use documents for these use cases. Another common scenario is gaming. It's not just about storing a gaming profile, but it's also about game management, matchmaking, and really tying all that together for a complete user experience for your gamers as they're advancing through their journey in a specific game or set of games. Personalization is also a common use case. We see customers customize offers based on transaction history or financial data to improve user experiences. In addition, with the scale that AWS and Amazon DocumentDB provide, we're also seeing customers deploy document databases for a much wider range of internet scale use cases, including critical customer-facing e-commerce applications and IoT solutions. Working backwards from our customer needs, with the use cases that were just mentioned in mind, we built Amazon DocumentDB with a cloud-native architecture designed for scaling enterprise JSON workloads with ease. Some of the pillars of the Amazon DocumentDB service include, number one, being fast and scalable. An essential design feature of DocumentDB is that it decouples compute and storage, allowing each to scale independently. Because storage and compute are separate, customers can add replicas without putting additional load on the primary instance. This allows you to easily scale out read capacity to millions of requests per second by adding up to 15 low latency read replicas across AWS availability zones in minutes. By adding up to 15 low latency read replicas across 3 AWS availability zones in minutes. DocumentDB's distributed fault-tolerant self-healing storage system auto-scales up to 128 TB per database cluster with zero downtime or performance impact to your application. With Amazon DocumentDB Elastic clusters, you can scale to millions of writes and petabytes of storage with little to no downtime or impact to your application. The Amazon DocumentDB service is also fully managed. Similar to our other AWS purpose-built database services, Amazon DocumentDB is fully managed so that you can scale your databases with clicks in the console rather than executing a planning exercise that takes weeks. With the service being fully managed by AWS, you can reduce administrative activities such as capacity planning and maintenance, get built-in high availability, backups are enabled by default, patching is automatic, and you can benefit from monitoring and alerting on your clusters or instances. Another component of the Amazon DocumentDB service is that it is enterprise ready. Amazon DocumentDB achieves the expressive document query support while also maintaining the high availability, performance, and durability required for modern enterprise applications in the cloud. Amazon DocumentDB Global Clusters provides disaster recovery from region-wide outages and low latency global reads. DocumentDB simplifies security by providing strict network isolation within your Amazon virtual private cloud. All data is encrypted at rest with AWS KMS, and encryption in transit is provided with transport layer security, or TLS. DocumentDB also has compliance readiness with a wide range of industry standards. The last area that we'll talk about is MongoDB compatibility. Because many of our customers with document database needs are familiar with the MongoDB APIs, we designed Amazon DocumentDB to implement the Apache 2.0 open source MongoDB APIs. This allows customers to use their existing MongoDB drivers and tools with Amazon DocumentDB and to migrate directly from their self-managed MongoDB databases to Amazon DocumentDB. We're just talking briefly and kind of reintroducing some of the service components. We do want to be clear. DocumentDB is not a drop-in replacement for MongoDB. So it's very important that you look at some of the tools that we created if you're looking to migrate from MongoDB to DocumentDB. Some of the tools that are available on our GitHub, which we will include following this event. Ultimately, there's a compatibility tool that will let you scan the logs of your current implementation and allows us to look and see if you're potentially compatible to run those workloads on Amazon DocumentDB. The last slide that I'll cover is just a brief snapshot into Amazon DocumentDB customers across the industries. So Amazon DocumentDB is being used today by a wide variety of customers, from longstanding global enterprises like Capital One, to digital natives like Rappi and Zulily, to game publishers like Habi. In addition, several products that Amazon customers use, such as the Fulfilled by Amazon experience on Amazon.com, are powered by Amazon DocumentDB. We have customers in virtually every industry, from financial services to retail, from gaming to manufacturing, from media and entertainment to publishing, and more. We welcome you to explore our customer page, where you can hear directly from our DocumentDB users on why they chose DocumentDB and how it has positively impacted their business. At this stage, we'll move on to some of our more lower level technical content, and Mihai will start presenting. Mihai, take it away.
Thank you, Jason. So for continuing this presentation about data modeling methodology, in order to understand the modeling, we need to understand how a JSON document looks like. As Jason, my colleague, mentioned in the previously, with Amazon DocumentDB, data is stored in JSON format. So JSON derives from JavaScript, hence the name, JavaScript Object Notation, which is an open standard file format with a lightweight composition, which makes it easily transferable from system to system. A JSON document uses a human-readable text to store and transmit data objects consisting of attribute value pairs and arrays or other serializable values. The basic data types can be string, can be Boolean, can be a number, integer or float, can be arrays or subdocuments. If coming from SQL, a document is like a row in a table that has been joined with other relevant rows from other tables. A field has an assigned value, just like each column in a row has a value. This is a powerful feature of document databases. Instead of having to query multiple tables and their related data and assembling it all together, you can keep the related data in a single document, which can then be retrieved in a single query. If we are thinking in programming language terms, a document can be viewed similarly to a dictionary or a map. Flexibility of the schema, I think this is probably the most appealing thing to developers, especially, because there's no need to predefine it in the database. Documents in the same collection don't need to have the exact same fields. And furthermore, the data type in any given field can vary across documents. This is a very big benefit. If you're doing an agile development, you can change things as the business requirements change as well. And those changes to the schema are easy to do and do not require downtime. Also, schema flexibility is a benefit if you're pulling data from multiple sources, helping with data ingestion as well. In other words, you can have multiple versions of your schema as your application evolves over time. And all the schema versions can coexist at the same time in the same collection. But having said that, that doesn't mean a schema should not be followed, even if it's just implied. Not having a schema optimized for the actual access patterns of the application can have a series of implications. So why is schema design important for document databases? Well, the first reason is what I want to what I like to call it schema. It's schema cohesion. It's good to keep an order, avoid the confusion, and follow a set of rules for the database schema. And again, I'm drawing a parallel to software development. It's like having a good code base that follows best practices and it's easy to understand. Similarly, a good schema will maximize your developer productivity and will be easier to create new features for the application or improve agility of application development. Second reason is having a good schema will help you avoid anti-patterns. Because with all this flexibility, it's easy to fall in this trap that everything can be added to a single collection, adding an unlimited number of fields to a single document schema. First of all, you'll end up with potentially very large documents, and there are some limits for how large a document can be. For example, with Amazon DocumentDB, the limit is 16 megabytes for a document. Or you may find that you'll store data in a document that is rarely needed by the application. Or because you have too many fields, you'll need too many indexes. And as you probably know, indexes do come with a cost, memory, storage, or write throughput overhead. And of course, an unoptimized data model will affect the performance of your database, while a good model will improve query latency and reduce I/O operations, which in the end impacts how the application performs and the overall end user experience. Lastly, a good model will impact your database cost. Typically, the first reaction when the database is slow is to scale up or out, bringing up the infrastructure cost. Or think about time spent by a DBA or a developer investigating a slow query. That can also translate to lost revenue. Now, before talking about data modeling methodology, we need to understand the concepts first. The first concept we need to understand is entity. So what's an entity? You can view it as an unique object that makes sense for your application or use case. If we take the example of an e-commerce application, an entity can be the product, the items being sold. You'll have orders and, of course, customers. This will be the entities to start with. But new entities can be added to your model depending on the requirements. For example, you may decide to implement reviews for those products. Then another entity can be reviews. Or maybe you want to have the payments data. Then that can be a separate entity as well. It all depends on the application requirements. And as we'll see throughout the course of this presentation, defining those requirements is part of the data modeling methodology. The second concept is relationships, which refers to the representation of how multiple entities are logically connected to each other. We can have one-to-one, one-to-many, and many-to-many relationships. In the e-commerce application example, we have several relationships, such as a one-to-many between product and reviews, since a product can have multiple reviews, but one review will belong to one product. But we can also have many-to-many, like the one between product and orders. Understanding the relations between the entities is very important for document database schema design, as this is one of the most important pieces of information for choosing between a normalized model and a denormalized model. So obviously, the next concept we need to understand is the normalized or denormalized schema modeling. And you probably heard of this before, but for document databases, we call this the embedded or the reference model. So what exactly does this mean? Well, the embedded means you store the data into arrays and objects or subdocuments within the same parent document. This means documents are all stored under one collection. And whenever you retrieve the parent document, you also retrieve all its embedded documents. So this would be the denormalized model. The reference model refers to splitting the data into two or more collections and reference or link the pieces of data to maintain the relationship. If coming from the relational world, you can view this as the normalized model. Both models have their advantages, but limitations as well. For example, the embedded model, the major advantage is that there are less calls to the database, as all the needed data for an entity is retrieved in a single query. Generally, this model provides better performance for read operations, since there's no need to join the data. But on the other hand, it can lead to large documents. And as I mentioned, there are limits. With larger documents, the working set will also be larger, which means memory requirements may be higher in order to cache the data, because otherwise you may see performance degradation, or you may have to upgrade and increase infrastructure cost. With the reference model, you will have smaller documents. The working set will be smaller, hence less memory requirements. But on the other hand, with this model, you'll have to perform more queries or joins to retrieve all the data needed for an entity. Lastly, the last concept we need to understand is design pattern, which is a reusable solution to a data modeling challenge. For example, when you may have repeated computations that require too much processing power, or when the documents become too large, a design pattern can be applied to structure those documents better and simplify the queries needed by your application. By applying one or more design patterns, you can optimize your access pattern, you improve the document structure, have less indexes required, and simplify your queries in general. So let's discuss about the methodology. There is a methodology, a set of steps to follow in order to define your schema, which are grouped into three major phases. The first one is to lay down all the application requirements and gather all there is possible to know about your data. The second one is to identify the entities and the relationships between them. This will be important when choosing how to model those relationships. And the third phase is to identify and apply design patterns to optimize the model and address performance requirements. All of this together should result into the schema model optimized for your particular use case. So let's describe each phase a little bit more. First phase, identifying the workload. In this phase, you'll find out how the data will be used for your use case. You'll have some input information to start with. It can be a requirements document or a scenario of the use case. If already started a proof of concept, or you are migrating from a different database, or you are refactoring an existing NoSQL model, you may also have some metrics and logs, which are very useful. And you can make assumptions, how much data or how many reads or writes the workload will produce initially or in a few months or years. Even if you get those numbers wrong, recording those numbers will allow you to observe if there's a major deviation once the workload is in production. When you observe those differences, it will be a good indicator that you may have to iterate again over your schema. So in this phase, you should be able to define the requirements, how you intend to use the data stored in the database, identify the queries, identify access patterns, how many reads versus writes are expected, identify the most important queries. So in that sense, defining or identifying the latency requirements for those queries would be a very good metric. Estimate the data size, either through metrics or assumptions. And finally, identify other requirements like consistency and tolerance to stale data. Decide basically if the application can work with eventually consistent data. If we take the example of an online blog website, you could start with a scenario. Gather all the input data, which can be, you can start grouping it like this. First, identify the operations and their type, if it's a read, if it's a write. Based on metrics or assumptions, you can estimate the frequency and average document size. And then you can add also the another important requirement like maximum latency. Based on this, you can extract some conclusions. For example, the writes frequency and average document size will allow you to estimate the data size. frequency and max latency will help you qualify those queries. For example, in this case, viewing a blog is the operation that occurs the most often at peak times and also has a requirement for the lowest latency. This will drive the design to reduce the number of queries when retrieving this information. For example, maybe use the embedded model as much as possible, or embed as much necessary information in the blog post to help reduce multiple queries from different collections. Second phase is identifying the entities and the relationships between them, which is one of the most important steps. Identifying the entities will allow you to determine the JSON key values for each entity and their value types. With the blog application, the entities can be authors, blogs, and comments. And the relationships between them, an author can post multiple blogs or comments. There will be a one-to-many relationship here, same as the relation between blogs and comments. But you can also have categories and tags, and the relationship between blogs and these entities is many-to-many. So how do you model this? How many collections you will have? What indexes? The biggest answer to be found after this phase is when to embed and when to reference. So let's see how you would approach this. The first thing to think about is to model by access pattern. If you're querying by author, for example, the simplest approach would be to embed everything in the author documents in an author's collection. But for the application, it's probably not going to be the best approach, as the UI, the front end, will show blogs, not authors. Also, from a database model point of view, the author's documents will potentially be quite large if an author writes many blogs, plus all the other data, the categories, the comments. Probably the better approach is to query by blogs, as this was also one of the requirements. One of the most important query was identified as being the reading a blog. So reading a read query, which is to fetch the blog data. In this case, the main entity is the blog, where you can embed all the related data, the authors, the categories, and so on. However, in this case, you might have some duplication of data, as the author's data will be duplicated in all the blog documents. Now, to avoid this, you can move the author's data to a separate collection and reference the author ID in the blog document. This will allow to query by blogs and authors. It will also be much easier to update whenever author's information is updated, since you'll not have to update every blog document posted by that author. Instead, you'll update just once in the author's collection. The other aspect to think about is to model by relationship type. And let's look at the relationship between blogs and comments. When there are just a few comments, it's fine to embed them in the blog document. But for a popular article with thousands or maybe more comments, things start to be a little bit different. From the application perspective, you could cap the amount of comments being fetched and displayed in the UI, but from the database perspective is an anti-pattern that should be avoided. When the relationship between two entities is unbounded, it's recommended to separate them into different collections. In this case, the relation between blogs and comments is one-to-many unbounded. To track the relationship between blogs and comments, you store the blog ID in each comment document associated with the article. In other words, storing it on the many side of the relationship. You'll have to do more queries, as you need to retrieve the comments for a blog from a different collection or use a join. But this way, you'll avoid having extremely large blogs documents. For the many-to-many relationship, you'll have two subcases. One is for when the relationship between the entities is bounded, and the other when the relation is unbounded. And let's take another example. Let's take the use case of courses and instructors. A course can have a limited number of instructors, and an instructor can teach a limited number of courses. In document databases, you can model this by embedding the list of instructors in each course document and the list of course IDs or subdocuments in each instructor document. This is known as the two-way embedding method. But in the case, if we take the other example of courses and students, there can be any number of students enrolled in a course. This represents an unbounded many-to-many relationship on the course side. The student side is bounded because the student will enroll only in a limited number of courses. In this case, it makes sense to model using an embedded list on the bounded side of the relationship. So you could store a list of course IDs or subdocuments in each student document. So based on what I presented so far, how can you choose between embedded and the reference model? And I have this. I have summarized here the things to think about when choosing between the two models. So if you have related data and you need to retrieve it in one query, or if you have a one-to-one relationship, or a one-to-many, but it's a bounded relationship, it's not the many side is not a huge number, it's a limited number, then the recommended model would be the embedded one. But if you have data that is rarely accessed, or on the other hand, you may have data that is frequently updated and also growing, and you have this one-to-many unbounded relationship, then the reference model makes more sense here. On the many-to-many case, then as you've seen, I've just shown you, it's pretty much a combination of the both models. So next, I have a demo showing the two models for an e-commerce use case. So let's watch this next. Let's see how the two models, embedded and reference, would look like. I have a simple example for an e-commerce use case, and I'm modeling the product entity. I'm connected to an instance-based DocumentDB cluster, and I have two databases, catalog embed and catalog reference. In the catalog embed database, there's a single collection called products. If I do a find all here, I have two documents which I've modeled this way with attributes like product ID, name, description, price, and so on, using various JSON data types from integer to string and array. Let me switch as well to a JSON view so we can see the schema in JSON format, which looks like this. It's a randomly generated data set which I've created for this example. I'll switch back to tree view. Notice that I have reviews array embedded in the product document. And the first product has 5 reviews, so there are 5 elements. But if you take a look at the second one, this one has 25,000 elements. And that's because the relationship between product and reviews is one-to-many unbounded. If a product, imagine, becomes very popular, it can receive an unknown number of reviews. If we are to look at the size of the document, and I have a command for this, which is in this one, and I'm filtering for product ID 2. Okay, let me clear this and run it again so we can see a little bit better. This is in bytes, so that's 8.8 million something bytes. That's around 8.8 megabytes, which is rather large. And although you can fetch the whole document with a single query, so I can do a find here and I can filter for product ID 1, or I should say 2, the one with many reviews. That's almost, imagine that that's almost 9 megabytes, which was transferred over the wire from the database to the client. Also, think about updating this document, which clearly it happens quite often, having 25,000 reviews and probably increasing. That can pose also some performance issues, since for every insert of a new review, the whole document has to be retrieved again. Notice also that I have attributes, which is also an array with 2 elements in this case. This will be the specifications of the product. I have size and weight for this example. Now this one can also be viewed as a separate entity, right? So the attributes of a product can be a separate entity with also a one-to-many relationship. Probably in the relational world, you would model this in a separate table. But because in NoSQL, because this is a limited relation and it's data that it relates to the product document, and you need that data all the time, it will now grow without a limit, and it's rather small, then you can embed that information in the parent document. But what do we do with the unbounded relationship that grows without a limit? Well, for that, the recommended approach is to use is to separate it, to move the many side, in this case reviews, to a different collection and use the reference model. So let's take a look at the catalog reference database where I've implemented this model. Here I have 2 collections, products. Notice that the reviews array is no more. That's because the reviews, I moved them to a separate collection, and every review, it's a separate document. Now, to maintain the relationship, I keep a reference to the product by having this product ID. So this will keep the relation between the review and the related product. Each document here, each review will have a product ID attribute. Now, to retrieve all the related information for a product, you have two options. One is to execute multiple queries and merge that data at the application level, or merge it at the database level using a join. So the first option will be to execute a query on products, get the product ID 1, and then you will do a second query on the reviews collection, again filtering by product ID 1, and then merge the data in the application. The advantage here, though, is that even though you are doing multiple queries, you retrieve smaller documents since everything is separated here. Another nice advantage is that it's easier to paginate, if you will, because you can limit, for example. So if you want to retrieve just a subset of the reviews, and if I filter for product ID, the one with many reviews, I can filter and retrieve just 5 reviews, for example, or just 10 reviews. And you can also do a sort, because probably you are interested in retrieving the latest review. So for that, I can do a sort on date, and I'm ordering this in a descending order. So you can do that as well, much easier. Now the other option is to, like I said, is to join at the database level. Amazon DocumentDB supports joins using the aggregation framework. The operator to use is called $lookup. Let's look at a typical aggregation pipeline. This will look like this. I'm using the aggregate method. The pipeline, the first stage in the pipeline is $match, which helps filtering the products, in this case, that I want to retrieve from the database, let's say product with ID 1. And the $lookup stage performs the join, which is a left outer join. In this case, matching the documents from the products collection with the documents from reviews. This from one will specify the collection I'm joining with. The equality match is done on the local field. Local field is the field in the left collection, the products collection, and the foreign field is the field or the attribute in the joined collection, in this case reviews. The name of the field is called product ID in both collections. That data is going to be merged in an array called reviews. I put it here, but I don't know, you can call it any way you want, call it reviews results if you want. Once I run this aggregation, this will retrieve the product ID, the document that matches the product ID, and with it creates this reviews array, which is data merged from joined from the other collection. As you can see, the model looks quite similar to the embedded one, just that in this case the data has been merged using the join capability. So this is in a nutshell how to design the schema for your data using the two models, embedded and reference. Now let's get back to the presentation and talk about design patterns. Now the third and final phase to the data modeling methodology is to identify and apply one or more design patterns. And I'll discuss some of them that can be applied to most situations. For example, the attribute pattern can be used whenever there are similar fields in a document. For catalog or inventory use cases, an item document may have different fields that refer to its characteristics, its attributes. If you want to search for all those attributes efficiently, then you'll need indexes. And in the initial iteration of the data model, you'll need several indexes, possibly for each attribute. By using the attribute pattern, we can move this subset of information into an array and reduce the indexing needs. The same data is modeled into an array of key value pairs. Indexing then becomes more manageable since only one index can satisfy queries for all the attributes. It's also much better organization of the item document, as this way it allows for non-deterministic naming, and adding different other attributes is much easier. So overall, a very good optimization just by recognizing and applying the right design pattern. The other pattern is called a subset pattern, which solves the problem of having the working set exceed the capacity of RAM due to large documents. If you remember from my earlier example for blogs and comments, the solution to the one-to-many unbounded relationship was to move the comments to a separate collection. But to optimize the number of queries or joins needed to fetch the documents, you could have a last comments array in the blogs documents, because typically users are interested most in the last comments. So keeping a subset of the related data in the main entity will reduce the need to perform an additional round trip to the database. If the user wants to see all the comments, then that would be a separate link in the UI that will translate to a separate requery in the comments collection. But by moving the unbounded data to a separate collection and keeping just a subset, you'll keep the document size small. The added benefit of having small documents is that the working set will be smaller, which means less memory requirements. The computed pattern can be utilized whenever calculations are needed to run against your data. Just to give you a simple example, let's imagine you have an items collections and you want to count the number of items in each category. You'll have to read all the items, then group per category and count documents for each distinct category. Instead, you could do what I call you can cache whenever a new item is added or an existing item is removed. Yes, that will require, let's say, an additional write query, but most of the applications are read heavy. And this way you are reducing or avoiding repetitive processing, and queries will become simpler and faster. This logic is very useful whenever you're doing mathematical calculations, sums or grouping of data or aggregations in a repeated fashion. When the application is read intensive, these computations are amplified, putting a lot of stress on the CPU, memory, and I/O for the instances of the database. The extended reference pattern optimizes the schema for when data has to be retrieved from multiple collections. For example, we may have the use case of an e-commerce application. One entity is invoices and the other entity is customers with a one-to-many relationship. You need customer information for each invoice. So to join, for that, you need to join all this data. And joining all this data may have a performance implication at the large scale. To reduce the join operations, one option would be to embed all the information about the customer in their invoice document, but that can result in too much duplicated information. With the extended reference pattern, you can optimize this. Instead of duplicating all of the information of the customer, copy just the most important fields and most accessed. To keep data duplication under control, duplicate only the fields that are needed and that do not change often. Full name, for example, is not something to change that changes often. Addresses may change, but on the other hand, in this case, it makes sense to keep historical data about the address at the time of the invoice. Overall, the extended reference pattern can be a great solution when your application is experiencing many repetitive join operations. Just pay attention to how you manage the duplicated data. The last pattern I wanted to highlight is the bucket pattern, which is typically used when dealing with a stream of data over a period of time, also known as time series data. Internet of Things is a good use case for this pattern. For example, if you want to store sensor information for temperature every minute, you could have a stream like this where every reading is stored as a separate document. However, you can end up with a large amount of documents, and to query efficiently, you'll need indexes on device ID and timestamp fields. The more documents, the larger the indexes, which will require scaling up or out much sooner. You can leverage the bucket pattern and restructure the document schema in this way. For an hourly bucket, you record the hour, and in an array, you record the temperature readings. This way, instead of having 60 documents per hour per sensor ID, you'll have only one document. The index will be on the date field instead of timestamp, so the index size will potentially be 60 times smaller. Furthermore, you can combine this with the computed pattern and also store a pre-aggregated data, for example, to calculate the average temperature for a bucket very easily. So the bucket pattern is a great choice, especially when dealing with time series data. It reduces the overall number of documents in the collection and improves index performance. And as you've seen, it can also be combined with the computing pattern to simplify data access. So let's summarize the main takeaways from this presentation. So the first one is to understand the application requirements. To leverage the benefits of NoSQL document databases, it's important to design data models that are application-specific in order to store the information in a way that optimizes query performance. Focus on access patterns and then on relationships when deciding between the embedded and reference model. Lastly, apply design patterns to optimize the model. But the first thing to understand is that data modeling, it needs to be an iterative process through the development or the life cycle of your application, instead of being a one-time task at the beginning of the application development. When adding a new feature or thinking about changing the model, do apply the methodology again. Also, from my experience, it's important to have a good collaboration between different business stakeholders, between the DBAs, the SREs, and the software developers, who are the people that translate the application requirements into actual code. Now, to learn more about data modeling for Amazon DocumentDB, we've put together a digital course. It's free to enroll for anyone. You can find it on the AWS Skill Builder website by scanning the QR code that you see on the left. And if you want to get started with Amazon DocumentDB, we also offer a free trial with the resources that you see on the screen. 750 instance hours, 5 gigabytes of storage, 5 gigabytes of backup. So with this, I want to thank you very much for your time and for joining this webinar about data modeling methodology with Amazon DocumentDB. I hope this was useful and it has given you a better perspective on how to model your data for optimum performance and cost.